In this video, we're going to talk about the spectroscopic analysis of aldehydes and ketones. A lot of this information we actually got last semester when we talked about IR and NMR spectroscopy, but particularly for IR spectroscopy, there's some additional information that we're going to talk about here that we didn't talk about so much last semester. So if you remember, typically what we expect to see when we have a carbon-oxygen double bond is a very intense, relatively broad peak in the double bond region. If you remember, the double bond region is between about 1600 and 1850 wave numbers. The other peak that we'd expect to see in this region is a carbon-carbon double bond. Generally, those are shifted to lower frequencies. They're not as broad, and they're generally not as intense. The carbon-oxygen double bonds are generally around 1700 to 1750 wave numbers. So generally, we see a strong peak, a little bit above 1700 wave numbers when we have the carbon-oxygen double bond. One thing we did talk about last semester is that when we had conjugation, when we had delocalization, generally that shifted the frequency to lower frequencies. And the reason for that is that we can draw several resonance structures where we have just a single bond between the oxygen and a carbon. Single bonds are longer and weaker than double bonds, and so that's going to shift it to lower frequencies in the IR. So when conjugation is possible, and we can draw multiple resonance structures with just a carbon-oxygen single bond, we'd expect the frequency to be lower than when we have just an isolated carbon-oxygen double bond. One thing we didn't talk about last semester was the effect of ring strain. And so here you can see with a six-membered ring, where we have relatively small amount of ring strain, the frequency is about where we'd expect it. But as the ring gets smaller and the ring strain increases, that tends to shift the frequency of the carbon-oxygen stretch to higher wave numbers. Another thing we didn't talk about last semester is the specifics of the aldehyde CH stretch. So this carbon is sp2 hybridized. And generally when we have an sp2 hybridized carbon with a CH stretch, that appeared around 3100 wave numbers. Aldehydes are somewhat unique, and the CH stretches actually appear well below other CH stretches. Normally an sp3 hybridized CH stretch is the lowest, and it's just below 3000 wave numbers, maybe somewhere around 2900. The CH stretch actually appears as a doublet. We generally see one peak around 2850 and another peak around 2750. And you can see those aren't quite exactly 2850 and 2750. So there is, some error in these numbers, or there's some slop in these numbers. The peak at 2850 is sometimes hard to see because it often overlaps with the other sp3 hybridized CH stretches. But when you have an aldehyde, the peak at 2750, or maybe a little bit below 2750, is often fairly noticeable. So if you know you have a carbonyl compound, if you want to know whether it's an aldehyde or a ketone, check and see if there's something around 2750, or maybe a little bit below 2750, and that's a good sign that you have an aldehyde. For the Proton NMR, there's not much more to talk about that we didn't talk about last semester. The C double bond O doesn't appear directly in the Proton NMR because, of course, it doesn't involve any protons, but other hydrogens that are adjacent to the C double bond O are shifted downfield about 1 ppm. So generally CH2 is going to appear about 1.2 ppm. If it's adjacent to the carbonyl group, that shifts it about 1 ppm downfield. Another thing to look out for in the Proton NMR of aldehydes is the aldehyde CH stretch does have a unique signal. And we generally have a singlet because it's not adjacent to any other hydrogens. It should have an integration of 1 because there's just one hydrogen, and it's going to be down around 9 or 10 ppm. This is fairly unique. There aren't many other signals that would be downfield that far. So if you have a singlet with an integration of 1 down around 10 ppm, that's a pretty dead giveaway that you're dealing with an aldehyde. And finally, for the carbon-13 NMR, this is a table that we saw last semester, and the C double bond O is about the only thing that appears that's de-shielded above 150 ppm. So if you see anything around 200 ppm, that is indicative of the C double bond O from the carbonyl group.